Okay, so today we'll discuss about elastic potential energy in a stretched wire. So in this chapter of elasticity, we'll consider suppose an cylindrical wire. This is suppose a wire, and if we stretch it by some load or some weight, then the energy, how much energy will be stored in this wire. We know that if the body will be deformed or some force will be applied on this wire, then the interatomic forces, they will try to come in the equilibrium position. So what will happen? Suppose I stretch this wire, the interatomic forces, they will bring together, they will try to come to the equilibrium, so that we are working against it and some energy will be stored on this one, on this wire. So quantitatively, if we want to calculate what will be the potential energy per unit length of this, per unit volume of this wire. Suppose this wire of, this is a wire of length L, let it be capital L. After I applied force on this wire, suppose I put some load on it, some weight to this one, then this wire gets elongated, its length increased to L plus small l. This length is suppose small l. The length increased to L plus small l, and area of the cross section of this wire is, let it be capital A, area of cross section. Okay, so we know that from Young's modulus formula, your Y is FL del L A. This is your Y or Young's modulus. Here del L we have taken as small l, that is change in length or increment of length. So I can write this equation like this, that force is Y small l A upon capital L. Okay, so this is the force when there will be elongation L. So if I want to calculate that, suppose for an infinitesimal increment, suppose an infinitesimal increment, let it be dl. For an infinitesimal increment, your work done dw f dl, f dot dl, or if f dl you can write, because cos 0 is 1, so force is along parallel to the area of cross section, so we can say theta is 0 degree, that is f dl, we can write f dl. So force we will put from here, that is Y L A upon capital L dl. So this is the small work done for the increment of an infinitesimally increment, very small increment dl. This much of work done or this much of energy will be stored on the wire. So if I'll integrate it, then I will get the whole work done. So if I'll integrate it, that is integration of dw, that is w will get, and integration limit we will take, that L small l starts from 0 to L become L, means this much increment. Okay, so this w work done, if I'll integrate it, integration from dl is the variable, so L from 0 to L, y a upon L, these are the constants, and small l dl. So its integration will be, or w will be y a upon L small l square upon 2, or I can write work done is half y into L small l upon capital L whole square. I divided to one capital L and will multiply one L into A. This length into area is the volume of the cylindrical wire, you can say. So here y is the Young's modulus, L upon L means small l, that is change in length upon original length is the strain of the material. So here you can write that your work done is half into Young's modulus into strain square into volume. L into A is the volume of the material. Now this much of work is done when I applied a force F on this object for the increment such that the increment is small l. For that, how much work is done? Now the work done is half into Young's modulus into strain square into volume of the object. This much of work is done, and this work done is exactly your potential energy restored in the wire. So this work done for the whole wire. Now if we will calculate potential energy per unit volume, so what will do? Now potential energy per unit volume, I will divide just volume. Now this is your potential energy, so I can write that potential energy per unit volume, let it this small u is half into Young's modulus y into strain square. Okay, so this is one formula. I can write in other way, that is half into Young's modulus y, I can write that is F L upon del L A, and strain is your small l upon capital L square. Here del L is L we have taken because change in length we have taken as small l. So I can write this capital L small l square will be cancelled. So F upon N is A is stress. Force per unit area is the stress of the object or stress of the material. So it remains F upon A into small l upon capital L, that means change in length upon L, that is strain. So I can write it that half into stress into strain. So work done per unit volume of the material is half into stress into strain, or you can say potential energy stored on the stretched wire is half into stress into strain, or you can say that it is your half into Young's modulus into strain square. In other way you can describe it in some next classes. I will describe some problems on this chapter, on this discussion. Thank you.